Okay, this chapter we're going to study rotational motion, centripetal motion, or circular motion, which includes centripetal acceleration and centripetal forces. And we'll end with gravitational forces, and we'll also have torque included. So there's a lot of different things that we're going to be studying in this chapter, but they all run well together. So the first thing today we're going to look at rotational motion. And this is looking at, like, as a bicycle tire goes around, what is the angular displacement? So how many radians has it gone through? We do measure this in radians. And so it's the change in angle of a rotating object, and we use radians. And so one full rotation is 2 pi. We also have angular velocity. So anytime we see angular, we are looking at the rotational part of that, whatever variable it is, whether it's displacement, velocity, or acceleration. I guess I should say angular, let's go back. Angular displacement, we use theta. We show that with theta would be the variable that we'd use, the symbol. Whereas angular velocity is represented by the Greek letter omega, which is W. It looks like a W, but that's omega. And it's the angular displacement divided by time. So here is the change in angular displacement divided by the change in time gives us the angular velocity, and that is radians per second would be our units. Now we can represent any of these and correlate them to the linear velocities, so by using the radius of the point of rotation. And so you look at the center of rotation to whatever point you're looking at on that axis, and that would be our radius. So the radius times the angular velocity gives us our linear velocity. We also have angular acceleration, so it's the change in angular velocity divided by time. So change in omega divided by change in time gives us alpha. This is the Greek letter alpha, and that represents angular acceleration, and it is in radians per second squared. And we can use the same type of equation to relate it to linear acceleration, where we're going to have the radius times alpha gives us the linear acceleration. So you can kind of see a pattern. All the equations of change in omega over change in time is very, very familiar to linear acceleration equaling change in velocity over change in time. And then the two equations are very similar in relating linear and angular quantities. So here's a chart that shows you the displacement, velocity, and acceleration. Linear, we use D, V, and A to notate the displacement, velocity, acceleration. And angular, we use theta, omega, and alpha. And this is how they're related to each other. It's all based on the radius. So what's the angular displacement of each of the following hands of the clock in 1 hour? So in 1 hour, how many times does the second hand go around? Well, it goes around once every minute, and there's 60 minutes, so it has 60 times 2 pi, or we could say 120 pi. The minute hand would only go around one time, so that would just be 2 pi. And the hour hand goes around 1/12 of 2 pi, or we could say 1/6 pi. Okay. These are angular displacements. We would represent them by theta. This one we're using linear acceleration, and we're looking for the diameter of the reel. So we have a linear acceleration of 1.58 meters per second. So if we were to watch him go down the road, that would be its acceleration. But the wheels speed up, rotating, at an angular acceleration of 5.23 radians per second squared. What's the diameter of the truck wheels? Well, to correlate the linear and angular acceleration, we have A is equal to R alpha, right? What do we know? 1.85 is a linear acceleration, which is A. 5.23 is angular acceleration, which is alpha. So if we take 1.85 meters per second squared over, we're going to divide alpha over, so we'd have 5.23 radians per second squared. We would be left with, let's see, what would that be? 0.354 meters. Okay, radians really doesn't have, it's kind of unitless, so it just would be meters as our answer here. Good. Okay, next problem is dealing with a truck towing a trailer that with wheels that have a diameter of 48 centimeters. And that's the trailer tires. How does the linear acceleration of the trailer compare with that of the truck? So the linear acceleration, the linear acceleration of the trailer, this would be like if you watch them go down the street, how fast their acceleration down the street. The truck and the trailer have to be the same, right? They have to be equal. The angular acceleration of the wheels of the trailer and the wheels of the truck compare. So the wheels of the trailer are probably smaller than the wheels of the truck. And so we can either, we can make it a thought problem, think about how fast they have to accelerate, how fast the wheels are accelerating as they rotate. The smaller tires probably have to accelerate faster than the bigger tires in order to go to the same linear acceleration. Or think about if we have alpha equals, wrong way around. It's A equals R alpha, right? Let's go check that equation real quick before. That just keeps going back and forth. Hold on. Where's that table? There it is. Yeah, A equals R alpha. Good. If we look at A equals R alpha, if our linear acceleration is the same, but the R goes down because the radius of the tires of the trailer are smaller, then that means alpha, our angular acceleration, has to increase in order to keep A the same. Okay, so the angular acceleration of wheels of the trailer, so alpha of trailer is higher than alpha of truck tires. Okay, you want to replace the tires of your car with the tires that have a larger diameter. After you change the tires for trips at the same speed and over the same distance, how will the angular velocity and number of revolutions change? So we have angular velocity, we have V equals R omega. So if our linear speed says same speed, so that would be, this would be the same. We have changed our tires with larger diameter, so that means our radius is going up. The speed of rotation goes down in order to go to the same speed. So our angular velocity, omega, goes down, and the number of revolutions would also go down. So the times around would go down. Okay, when a machine is switched on, the angular velocity of the motor increases by 10 radians for the first 10 seconds before it starts rotating with full speed. What's the angular acceleration of the machine in the first 10 seconds? Angular acceleration, alpha. Our equation is change in omega over change in time. So for the first 10 seconds, it increases by 10 radians per second, so 10, and the time period is 10 seconds, so we would have 1 radians per second squared. Okay. And that's all we're going to do today. We'll start tomorrow. We'll talk about circular motion, and then we'll go into next week. Yeah, probably next week we'll do the gravitation. And your worksheet here, we have some problems on rotation, and that will be due tomorrow.